So then when we're computing this new matrix, this cell would be depending on garbage values here in this layer. But this cell, because he depends on just these guys, would be fine, right? So what would happen is that we would actually get an even more inner rectangle that is valid, and then 2 layers of rows that are invalid. Now we can use this idea to do multiple iterations without having to copy cells over. So suppose we have a really big universe matrix with several built up layers of extra values that we've copied over. Now here, if we have 2 layers, that means that we can do 2 iterations without doing a copy. This idea of going multiple iterations in between copies is not particularly useful in the padding case. When we're just doing padding, one iteration between copies tends to be just as good as 2. But when we're doing communication between processors or between nodes, the cost of this copy between nodes and processors tends to be very large. And so you want to have as few of those as possible. And so if we can do a lot more iterations between each communication, this actually does start to help a little bit. Okay, back to the padding code. Here we lay out a framework for us to do our multiple layers of padding. So we have a little bit of macros here describing what's going on with how many layers of, we call them ghost cells, there are. So in this case, we're not going to actually use multiple layers of padding. Later on we might. The out ghost is how many valid layers in the new matrix will there be, and the in ghost is how many valid layers in the universe matrix will there be. There's a lot of optimizations going on in this file, so I'm going to go through each one as I see them. The first thing that we're going to do is, because we're storing only zeros and ones in each cell, we don't need to use a full unsigned integer like we've been doing. We can actually just go ahead and use a 8-bit integer type, which is the smallest the system will let us use, and the smallest the system can deal with quickly. So this uint8 type, we allocate a uint8 universe and a uint8 new matrix. Then we go ahead and we pack our 32-bit types into our 8-bit universe. The benefit of using these values is that the cost of loading values from cache depends on only the number of cache lines that you have to load. A cache line is, about 64 bytes. So if we can pack a bunch of values into those 64 bytes, we're in good shape. We can actually do more computation with the memory that we've loaded. So by making the type smaller, we can do more computation, or the same amount of computation, for less memory cost. Now that also applies to what I'm doing down here. I'm copying the uint8 types, I'm copying them into the ghost cells, like I explained earlier, and I've done it in kind of a complicated way that will be easier to parallelize later, so I'm doing it row by row. And the important thing about this copying is that I'm copying word by word and not uint8 by uint8. So that allows me to move 4 uint8s at a time, which is also useful. I mean, I'm doing less logic in this copying of memory. Now let's look at the inner loop. This is the most important part of the code, and it's where it spends the most time. So, as you'll see, this inner loop looks a lot different than the way you remember it. The first thing you might notice is that we got rid of those 2 nested for loops that iterated over the neighbors. Instead, it's actually a lot faster to go ahead and just write out each iteration of the loop. This way we can avoid double counting our cells. Here instead we just store the value of our own cell in a variable called alive that we can use later in the logic. And it also removes the work that the compiler, or that the computer had to do in order to, add 1 to the loop increment variable and check whether or not it was less than 3, etc. The CPU likes to process instructions sequentially. So any kind of work that we can do to remove branches in the program will allow the CPU to better prepare for what instructions it's about to process next. Branching statements include ifs, switch cases, or loops. Another reason that loop unrolling is useful is that you'll see now these offsets into memory are constant. There's no complicated modular arithmetic. We can just say, look at this pointer and go, 0, 1, or 2 uint 8s off of it. This allows the compiler to better predict where the memory accesses are going to occur. And of course we have the same pointer swapping, and at the end we're going to have to unpack our tiny little types into bigger types. So let's see how well the padded code
How
can do.
much faster do you think it's going to be?
And of course, I'm going to cut the time that it actually takes to run this. It takes a while, but let's see what it does. And we're back. It looks like the padded did pretty well. We got a speed up of 4 over the reference version, which is looking good.
4 days down to 1 day, wouldn't that make
Next time
a
we move on to
difference?
the next optimization. Looks like next optimization is using SSE2 intrinsics. So most of the time people try and get their code to automatically vectorize. For me, I feel that oftentimes I can get better performance, or sometimes it's just difficult to get the code to automatically vectorize. So I'll go ahead and write those vectorized intrinsics myself. So if you haven't heard what SSE is, I'm going to remedy that with a couple of rectangles. So vectorized instructions are, they allow you to perform the same operation on multiple pieces of data at once. So essentially the vectorized instructions use vector registers, which store multiple copies of the same piece of data. So this was a normal register here. You have a vectored register might have 2 values in it. And so like operations that you could perform with your double-wide vector register is, say, you could do an addition, right? So here you could add XMM0 to XMM1, store the result in XMM2. And of course, this value would be the sum of this value and this value. This value would be the sum of this one and this one. And you can do this addition in the same time it costs you to add 2 numbers with normal instructions. So that's the benefit of using these. So SSE instructions can hold 128 bits. That means that they can hold 2 doubles, or they can hold 4 floats, or they can hold 4 uint 32s, or in our case, we can get 16 uint 8s. So we're going to be able to do our operations on 16 uint 8s at one time. Now you might be wondering, Peter, how are we going to actually compute game of life using these vector registers? Well, when we're adding up the neighbors, we can actually add up the neighbors for 4 cells at a time. I'm going to show you how with a couple of rectangles. So let's assume, for simplicity, that our SSE vector register holds 4 of our cells. Now, this guy, let's assume that this vector register represents the sum of the neighbors in each cell. And let's assume down here that we have 4 little cells in a row. Well, the first thing we're going to need to do is we're going to need to add the upper left neighbor of this cell, which is right here. But while we're doing that, we can also add the upper left neighbor of this cell, which is right here. And we can add the upper left neighbor of this cell right here, and this cell right here. Now, all of these guys actually fit into a vector register without having to do any work. We can just load them into the vector register and add them to this guy. Now, the next thing we need to do is add all of the neighbors that lie immediately above all of these cells. So we can go ahead and add this neighbor, and this neighbor, and this neighbor, and this neighbor. Now, all of these guys can be added to the guy up here. In most cases, you should try to automatically vectorize your code. Generally, if you make your code simple enough for the compiler to understand, it can figure out how to vectorize it. However, if you don't know how vectorized code looks or how to structure your code into a vectorized fashion, it might be difficult for you to understand how to structure your regular code so that the compiler can automatically vectorize it. So I'm going to show you what the vectorized version of our game of life code looks like. We have our unrolled loop, and all of the operations are the same, except this time we got to spell them out for the compiler. So what we're saying is add a whole bunch, add all of our 16 8-bit types together by loading this value from memory and put it into this vector register here. And so we have a couple of complications in our code, but the logic and the same idea of the code is pretty much preserved here in this inner loop. One complication of using vectorized intrinsics is that you'll have to figure out how the end of your loop works. For example, if I'm processing 16 cells at a time, what happens if the grid is not a multiple of 16? In my case here, for simplicity, I assume that it is, but it's not a general solution. If you want to handle the edge cases, typically people just use regular code. You don't have to use the vector intrinsics, and you can just go ahead and handle those separately. And the code comes to an abrupt end. So let's see how well our SSE actually did for all of that complication of the code got.
How fast do you think this is going to be?
And if you haven't gotten the gist of it by now, most of optimization is trying things and seeing if they work, and oftentimes they don't. Here, you're lucky because you get to see a bunch of successful optimizations in a row. But most of the optimizations I tried here did not work, and typically a lot of this is just banging your head against the wall and calling your benchmark routine over and over again to understand which things help the code and which things hurt it. Oops. Okay, see that. Anyways, and this finishes around the back. On the back, and the SSE code looks pretty good. We have a speed up of 46 times over the reference version, which means that over the padded version, adding SSE instructions sped us up about 11 times. Now that's not as good as we could have hoped, given that the SSE instructions process 16 characters at a time. Now that we've all mastered SSE intrinsics, I can move on to the AVX intrinsics. Now these are no different than SSE, they're just twice as big. For that reason, I'm going to spare you the code and just look at how it performs. Okay, and as expected, the AVX code did a little bit better than the SSE code. Now, it didn't do 2 times better, but it did around that much, and that's about as much as I would have hoped. The reference time took 300 seconds, and our AVX code ran in 4 seconds. And we haven't yet taken advantage of multiple processors. So let's go ahead and do that. The first parallel implementation of life we'll cover will be in a shared memory programming model. In a shared memory programming model, it looks like each processor has access to the same copy of memory. However, this is an illusion, and the internals of communicating in order to keep everybody's copy of memory up to date is handled by the implementation of the operating system. In our case, we're going to use OpenMP to parallelize computation of our life grid. You can imagine our life universe is a rectangle, OpenMP works by parallelizing along loops. We have a particular loop, the loop along rows, that is an easy target for parallelization in the OpenMP scheme. So we have 4 processors. You can imagine partitioning the iterations of the loop into 4 blocks. Well, processor 1 would handle this rectangle with the grid, and so on with the other processors. Communication, although it doesn't look like it's occurring, is actually occurring when processor 2 reads a cell in processor 1's area. So for example, if processor 2 had to compute this cell in the new version, would have to read these cells from 1.
This is where the communication occurs. The programmer doesn't have to do this explicitly, it will be handled by the implementation. Communication occurs along these boundaries between the various sections that each processor is responsible for computing.
And even though OpenMP is handling communication along these boundaries, we still have to use padding in order to get the wrapping around effect and keep the high performance that we had in the serial case.
You may wonder why we chose to parallelize over rows and not over columns. The reason for this is that our universe matrix is stored in row major order, meaning that rows are stored contiguously in memory. If we parallelized over columns, our cache lines would be split along the boundaries.
Here in our OpenMP implementation, you'll see that we're using 4 layers of ghost cells.
We found that using 4 layers of ghost cells gave us better performance. I'm not 100% sure why this was, but my guess is that because the OpenMP parallel processing sped up the iterations so much, the cost of a copy in comparison became larger, so it made sense to do more computation and less copy. Most of optimization is trying a whole bunch of stuff and a whole bunch of different values and parameters and seeing what works.
Not much has changed in our OpenMP version until we hit the main loop. Now, even this loop looks the same. All we've done is added a couple of these pragma OpenMP parallel directives. So, pragma OpenMP parallel is the directive that spawns the threads. This actually starts the multiple processes up and running.
This pragma OpenMP4 is what actually divides the labor along the row blocks. Here you can see it acting along the rows.
Because we're using 4 ghost cells, we can afford to do 4 iterations of our life computation. So that is this loop here. We put the pragma OpenMP parallel directive out here so that we didn't spawn threads for every one of those 4 iterations. Instead, we can reuse the threads for each of these computations. To avoid race conditions, we have to assign only 1 thread to do the pointer swap.
And I'm back. It looks like the OpenMP sped up our code by a factor of about 2. Now, that's not quite as good as we could have hoped. We have 4 processors.
But getting full utilization of an OpenMP implementation is usually a rare occurrence.
The second parallel model that we'll cover is distributed memory model. In a distributed memory model, it looks like each processor has a separate copy of memory, and they have to communicate to each other explicitly with important information. To give you an idea of what that looks like, imagine each rectangle that I'm drawing represents a different portion of the universe. So we're going to split our universe up into 4 equally sized rectangles. Now we can assign 1 processor to each rectangle. But because this is a distributed memory model, processor 1 only knows processor 1 only knows area in processor 1's territory. So if processor 1 needs to read a cell in processor 2's territory, the 2 processors have to communicate that kind of information. So an easy way to represent this communication is to use a layer of ghost cells surrounding all of your rectangles, surrounding all of your territories. So this layer of ghost cells represents, it represents the cells that we would see if we actually did move into our neighboring territories. So, for instance, when one looks into this column of ghost cells, one is going to be seeing this column, this leftmost column of 2's territory. This also allows us to wrap around. If one is looking into this topmost layer of ghost cells, those ghost cells will hold the contents of the bottommost row of 3's territory. And you have to explicitly communicate these ghost cells between the processors. Because that's so expensive, it actually does help to have multiple layers of ghost cells in this situation, so that you can do many computations before having to pass ghost cells around. If we parallelize like we did with OpenMP by going along rows, then the communication occurs at the boundaries here. However, if we parallelize as we did in our distributed computation, then the communication goes along the boundaries of these cells. Now, as we add more processors to this case, the communication cost per processor stays the same. If I keep adding rows, the length of the row is the same, even though we have twice as many processors, they still have to communicate the same amount. Now here, if we add more processors, the perimeter of each processor's territory shrinks. They have to communicate less. So this scheme on the right-hand side is actually a little bit more scalable than the one on the left. However, the one on the left is a lot easier to implement. You can just throw the little pragma in front of the for loop. The other thing that we can do is if we're using MPI to do distributed computation along a whole bunch of cells like over here, we can actually use OpenMP inside of each cell to make inside of each territory to make each territory's computation go faster. This provides us a nice way to map our computation onto a traditional supercomputer model, where there's many nodes, each node having many processors. So the first thing you'll see is, the first thing that's different that you'll see is that there's a bunch of tags here at the beginning of the MPI file. And this is because if there's only 1 or 4 processors, pairs of processors might send more than one message between each other. For example, in the 4 processor case, messages will be sent between territories and wrapping around the grid between territories. So we need to use these tags to identify the messages. Most of the code is the same until we reach the initialization. So we have to start by sending the initial data to all of the processes. And we can do this using an MPI scatter, which is actually kind of a complicated call, but that's the price you pay for using MPI. The next thing we'll need is a bunch of intermediate buffers in order to hold all of our messages. So that's what's happening here. And we need a couple of MPI requests so that we can wait until our messages have been received by the appropriate parties. This is where we actually perform all of the sends to all of our neighbors in a very cardinal and diagonal direction. The details of how we actually call the MPI in order to send the data along the cardinal and diagonal directions are not they're not too exciting, so we're going to kind of skip over them. Just know that this portion of the code is sending and receiving the data to fill out the ghost zones. However, the inner loop in our MPI code looks exactly the same as it did in our OpenMP version. So we can actually we can have a little bit of local parallelism on each node. However, since I don't have access to institutional computing resources at this point in time, I won't be able to show you the multi-node MPI run. You'll notice that we did all of our sends and then all of our receives, then we computed the next iteration, and then we waited for new information.
We wait at the end of the program instead of at the beginning in order to interleave communication cost and the computation cost. So while we're computing the next iteration of life, we're also waiting for our messages to be received. At the end of the program, we use a gather in order to gather all of the results from all of the different processor territories and return them to the caller on thread 1.
Well, we ran our MPI program and it looks like it did about as well as the OpenMP did. We got a speed up of 156 over the reference version. And that's about as far as I'm going to go with this. You guys are certainly welcome to take it farther. Again, the code is on GitHub and you guys can check it out. And feel free to email me if you have any questions about the code. I hope this video inspires you to try some of these tricks on your own code.
Okay, so we went over all the typical tricks of the HPC trade. This is actually what is used in stencil calculations. So there's a couple nodding heads. They've seen a lot of these tricks. Maybe there's some new ones in here. But this is sort of your performance tool chest to make codes run fast. Different domains use other, different like particle codes and use different tricks. I'm going to turn it over to Andree now, and he'll talk about the computing systems that are behind all of this.
All right, so I'm Andree. I get the last half hour of your time, so I know you're all ready to go. I'm actually not a Seahawks fan. I'm just wearing it because it was the most offensive color I had in my closet this morning, so that you wouldn't fall asleep on me. But this is all very interesting. I know you've been inundated all day with information about high-performance computing, about programming, about studies and things like that. And for me, as a computer scientist, things kind of changed a little bit. I've been always interested in computer hardware. I've also done software and programming. I taught programming for many years here at UNM as well. And about, 10 years ago now, I received an email while I was a faculty member here at UNM saying, we're looking for a summer instructor in Los Alamos. We want somebody who teaches a systems administration for supercomputing class. Since they didn't have anything better to do during the summer, I thought, well, maybe I'll apply. And I don't know if you got an introduction to Gary Grider, but he was sitting later back in the room here. He came in and essentially said, here's some course material. Slapped a binder that was like yay thick, about 2,000 slides in there, and said, here, this is what you're going to cover in the next 10 weeks. And that was a very sort of interesting way of being introduced to high-performance computing. The main difference between what I was used to compared to what I'm doing now, right, is that it's not hard to administer one computer. I don't know if you've done it, you've maybe installed your own Linux box or Windows machine or whatever it is, and that's great. The question is, could you do 5,000 at the same time in one room, right? What this summer school did was essentially saying, well, if you're going to install a piece of hardware or a piece of software on 5,000 computers, are you really going to say, SSH node 1, yum install htop, right? And then wait for it to finish and then exit and then say SSH node 2, yum install htop, right? No, you're probably not going to do that, right? But oftentimes, if you haven't seen scale, this makes things a little bit more complicated because you may not know the tools that are available for you to do these kind of things. There's parallel SSH, you say, from node 1 to 5,000, install this piece of software. You wait 10 seconds and then it's done, right? It's a little bit more efficient. Now, this is a completely different way of looking at supercomputing compared to, I'm a scientist, I'm going to write my application, I'm going to log on to the head node, I'm going to say, run on 500 nodes, this application, and then you analyze and see how fast it runs. So I actually have, this is the only slide I have. So I'm not